Autonomous vehicles are among the most transformative innovations in modern transportation, promising to reshape how people and goods move across cities, highways, and even rural areas. At their core, autonomous vehicles combine advanced sensors, artificial intelligence, connectivity, and control systems to reduce reliance on human drivers. The technologies behind autonomy are diverse, ranging from basic driver assistance features to fully self-driving cars that require no human input. Understanding these technologies, their strengths and weaknesses, the challenges they face, and the opportunities they present is essential to grasping the future of mobility worldwide. The framework most often used to describe autonomous driving is the SAE International Standard, which defines 6 levels of autonomy from 0 to 5. Level 0 represents vehicles with no automation, where the driver has complete control. Level 1 introduces driver assistance such as adaptive cruise control, which automates a single function but requires the driver to remain engaged. Level 2 expands to partial automation, combining steering and acceleration or deceleration, but still requiring the driver to supervise at all times. Tesla's Autopilot and GM's Super Cruise are examples of Level 2 systems. Level 3 introduces conditional automation, where the vehicle can handle driving in certain conditions, such as highway traffic jams, but requires the driver to intervene when requested. Audi's Traffic Jam Pilot is a notable example. Level 4 represents high automation, where vehicles can drive themselves in geofence areas without human input. Waymo's robo-taxis in select U.S. cities are examples of Level 4 autonomy. Finally, Level 5 is full automation, where vehicles operate independently in all conditions without steering wheels or pedals. This level remains a vision of the future, as no commercial vehicles have yet achieved it. The technologies that enable autonomy are complex and multifaceted. Sensors form the foundation of perception systems. LiDAR provides three-dimensional mapping of surroundings. Radar detects objects and measures their speed. Cameras recognize lanes, signs, and pedestrians. And ultrasonic sensors handle short-range detection for parking and low-speed maneuvers. Artificial intelligence and machine learning interpret this sensor data, predict behavior, and make driving decisions in real time. Neural networks improve as they are exposed to more data, allowing vehicles to handle increasingly complex scenarios. Connectivity, often referred to as vehicle-to-everything or V2X, allows vehicles to communicate with infrastructure, other cars, and even pedestrians. This supports traffic efficiency and safety by enabling vehicles to anticipate conditions beyond their immediate sensors. Mapping and localization are also critical, with high-definition maps combined with GPS ensuring precise navigation. Finally, control systems and redundancy provide backup steering, braking, and power systems to ensure safety in case of failure, which is especially important for higher levels of autonomy. The advantages of autonomous vehicles are compelling. Safety is perhaps the most significant, as autonomous systems have the potential to reduce accidents caused by human error, which accounts for the vast majority of crashes today. Efficiency is another benefit, with optimized routes and smoother driving reducing congestion and emissions. Autonomous vehicles also promise greater accessibility, providing mobility for elderly and disabled populations who may not be able to drive themselves. Environmental benefits are possible as well, since smoother driving reduces fuel consumption and emissions, particularly when combined with electrification. Economically, autonomous vehicles could create new business models, such as robo-taxis, autonomous delivery services, and freight automation, reshaping industries and employment. Yet, the drawbacks and challenges are equally significant. The cost of developing and deploying autonomous systems is extremely high, with LiDAR, advanced AI, and redundancy systems adding expense. Job displacement is a concern, as driving-related professions could be reduced or eliminated. Safety remains an issue, as the technology is not yet foolproof and accidents involving autonomous vehicles have already occurred. Regulation is another challenge, as governments struggle to define liability, safety standards, and legal frameworks for autonomous driving. Public trust is also a barrier, with skepticism about whether autonomous vehicles can truly be safe and reliable in all conditions. Cybersecurity risks add another layer of complexity, as connected vehicles are vulnerable to hacking. Despite these challenges, opportunities in the near future are abundant. Urban robo-taxis are already being tested in geofenced cities, offering autonomous ride-hailing services that could reduce traffic and emissions. Autonomous freight is another promising area, with long-haul trucking and platooning reducing costs and improving efficiency. Last-mile delivery is being explored through drones and small autonomous robots, which could revolutionize logistics. Public transit automation is also advancing, with autonomous buses and shuttles being tested in smart cities. Integration with smart infrastructure, including vehicle-to-grid and vehicle-to-everything systems, could further optimize energy use and traffic flow. These opportunities highlight the potential of autonomous vehicles to reshape not only transportation, but also energy and urban planning. Regional adoption patterns vary widely. In North America, Level 2 systems are common, with Tesla leading the way, while Level 4 pilots such as Waymo and Cruise operate robo-taxis in select cities. Investment in autonomous trucking is strong, reflecting the importance of the freight in the U.S. economy. In South America, adoption is slower, with Level 1 and Level 2 systems more common. Infrastructure and regulatory challenges limit progress, though Brazil and Chile have begun pilot projects, particularly in urban buses and logistics. Europe has strong regulatory frameworks and is testing Level 3 systems, with companies like Audi and Mercedes-Benz leading development. The European Union also supports autonomous public transit and V2X integration, making Europe a leader in regulation and infrastructure. Asia is perhaps the most advanced, with China operating large-scale robo-taxi pilots through companies like Baidu Apollo and AutoX. Japan focuses on autonomous shuttles, while Korea invests heavily in smart city integration. Africa presents a different picture with limited adoption due to infrastructure gaps. Level 1 systems are most common, though South Africa has shown interest in autonomous mining vehicles, where controlled environments make automation more feasible. In conclusion, autonomous vehicle technologies are advancing rapidly, with Level 2 systems already mainstream and Level 4 pilots expanding in North America, Europe, and Asia. South America and Africa remain in earlier stages, constrained by infrastructure and regulation. The future promises robo-taxis, autonomous freight, and smart city integration, but challenges in cost, safety, and public trust must be overcome. The global race toward autonomy reflects regional strengths: North American innovation, Europe in regulation, Asia in scale, South America in emerging pilots, and Africa in niche industrial applications. By 2035, autonomous vehicles could redefine mobility, making transportation safer, more efficient, and more sustainable worldwide.
Fleet Mobility Today.